In this segment, we're going to look at how to use chain hashing to implement the dictionary ADT. So let us recall what the dictionary ADT is all about. Let U be a universe of either finite or countably infinite keys. And so each item that we want to store in the dictionary is identified by a unique key. Our goal in the dictionary, in implementing the dictionary ADT, is to store any subset D of this universe of keys, and it must be stored in such a manner that you can search and retrieve those keys quickly. You may have studied balanced binary search trees, and which are very good ADTs, dictionary ADTs. You may have also studied earlier on, you may have studied arrays and linked lists, which also can serve as dictionary ADTs. What we're going to look at today is how to use hashing, in particular the data structure called chain hashing, to implement a dictionary ADT. So in chain hashing, we have a hash table with n-1 cells in it. And we also have a hash function, let's call that h, and this hash function maps u to the range of indices of the hash table. So whenever we need to store an item, let's say x belonging to u, all we do is we apply the hash function and store the element x in the index h of x. Okay, but eventually we are likely to find some other item that's also going to hash into the exact same location. So what do we do at that point in time? We simply extend the list of items stored in that particular location h of x. And how do we do that? Well, we just maintain a linked list. So let's say we have two items x and y whose hash values are the same. Then let's say that x is already in the hash table, and then we encounter y, and y needs to be added to the hash table. So then what do? We insert the item y into the linked list, which is pointed to by the location h of x in the hash table. And in this manner, the items that hash into a particular location are stored as a linked list. And so your final picture would look something like this. Based on the ways in which the hash function works and the list of items that need to be stored in the hash table, chain hashing based hash table, you will notice that some of the linked lists are going to be somewhat long, while others can be fairly short, and even some of them can be missing. And so we are obviously interested in understanding how this, in analyzing and understanding how this chain hashing works. What are its qualities? In particular, we are interested in the query time. How long does it take to search and retrieve an item? So how does that even work? So let's say we have an item Z, and we need to find out whether this item Z is in the hash table. What do? We look at h of Z, and that's the index h of Z in the hash table. And then so that index is going to point us to a particular location in the hash table, and from there we see a linked list, and we follow the links in the linked list to see if the particular item Z is present in the hash table or not. So we would go here, and is that a Z? If that's not a Z, then we'll go one step further, and we either find Z there or we don't find it, in which case we just say Z is not in the dictionary. And if it is there in the dictionary, we're in a position to retrieve it. So that's how the queries work. And as you can imagine, the queries on average are going to be m over n, uh, where m is the size of the dictionary, or simply the number of items that are stored in the dictionary. And of course, n is the size of the hash table. But unfortunately, this is only on expectation. And of course, our big concern now is what about the worst case? How does chain hashing work in the worst case? So, how do we go about analyzing that? Well, here's where the balls and bins paradigm would be of help. Before we go about analyzing chain hashing, we have to be clear about some properties of the hash function that we use. In particular, we're going to assume a fairly strong property about the type of hash functions that we use. This is called the simple uniform hashing assumption. And what does it mean? It has two parts to it. Firstly, the probability with which any item x from the universe gets mapped onto a particular location I within the hash table is exactly equal to 1 over n. So uh, the hash function chooses the index I uniformly at random. And just to clarify, this doesn't mean that each time x is hashed, it will be any one of the n items equally likely. No, h of x will always be a particular value, but that particular value will be equally likely to be any one of the n locations. But if you were to hash the same x again, it's going to fall into the same location over and over again. So each invocation of the hash function isn't going to lead to a different location. It just means that when you hash a particular item, when you don't know anything about where it's going to land, it's equally likely to land in any one of the n location. So this is uniformly at random part of the SUHA assumption. The second part to SUHA is the independence of each hash value. So if the hash value f of x for each x must be independent of each other. In other words, the fact that f of x mapped to a particular location should have no bearing on the location to which another item y maps to. Notice that there is a little bit of tension here. What is that tension? Well, on the one hand, each time you invoke the hash function for a particular x, we have to deterministically get back the same hash value. However, the behavior of the hash function should be random. So for each value x from the universe, when you hash it, the probability with which it falls into any one of the bins must be equally likely, and they must be independent of each other. These are all classic things that we see with uniformly at random choices. And so how do we combine these two? Well, there's a lot of literature on that, and that's beyond the scope of our current lecture. So we're not going to delve into that per se. But what we are going to instead do for our purposes is just make this assumption that such a hash function exists, and that's what we are using. And our entire analysis is going to be built on this simple uniform hashing assumption. And as you can imagine, we're going to use balls and bins to view this chain hashing problem. We're going to view each location of the hash table, each location in the hash table as a bin. And each item that is stored in the dictionary is a ball. And this ball is thrown uniformly at random into one of the bins, and that's by virtue of our assumption that the hash function maps an item from the universe into one of the locations within the hash table chosen uniformly at random. And to simplify the analysis, we're going to assume that the hash table size, that is n, is chosen to be exactly equal to the number of items that we want to store in the dictionary. In other words, m equals n. Under these assumptions, we are interested, first of all, in the event that bin number 0, in other words, the very first hash location, gets k or more items. The question is, what is the probability of this event? And that's upper bounded by n choose k times 1 over n raised to the k. So the n choose k will isolate some k items from the list of items that we're storing in the dictionary, and there are n choose k ways of doing it. And once such a subset is chosen, each ball in that subset should fall into bin 0, and that is 1 over n raised to the power k. Notice that we are potentially overcounting the probability here because what we are interested in is the event that bin 0 receives more than or greater than or equal to k balls. What we have on the right hand side is we're isolating each of the k subsets and applying a union bound over all those k sized subsets. And this n choose k times 1 over n raised to the k can be expanded. In fact, this is an equality. Can be expanded into n times n minus 1 times and so on up to n minus k divided by k factorial times 1 over n to the k. Notice that the numerator here is at most n to the k. So this whole quantity is upper bounded by 1 over k factorial. And this in turn is upper bounded by e over k, the whole raised to the power k. How do we get this? We know that e to the k can be expanded using the Taylor series. And we will get the summation to be summation over from I equal to 0 to infinity k raised to the I divided by I factorial. But in that summation, let's isolate just one term. So that's the term k raised to the k divided by k factorial. So that's when I will equal k. So obviously if you just isolate that one term, the relationship here is going to be a greater than or equal to. And of course this will imply that 1 over k factorial is at most e over k divided raised to the power k. And this inequality that we get over here is exactly the inequality that we use over here. So far we've only focused on bin 0, but if we want to include all the bins, we simply apply a union bound over all the bins. And so we get the probability that there exists a bin with at least k balls is at most n times e over k whole raised to the power k. And from here, it's a simple exercise, and I encourage you to work it out. It's a simple exercise to show that this quantity is at most 1 over n when k is at least 3 ln n over ln n. And this is in fact one of the most classic balls and bins results. If you throw n balls each into a bin that's chosen uniformly and at random and independent of each other, if you throw these n balls into n bins, the height or the number of balls that fall into the bin with the most number of balls is at most 3 ln n over ln n with probability 1 minus at least 1 minus 1 over n. In other words, the height of the max loaded bin will exceed 3 ln n over ln n with probability that is upper bounded by 1 over n, which is the way we have stated it over here. So applying this result back to the chain hashing context, we can conclude the following. When m equal to n, that is when the size of the hash table is designed to equal the size of the dictionary that we want to store, then with high probability, that is probability of the form 1 minus 1 over n, the query time will be less than 3 ln n over ln n. So this is significantly less than what you might normally imagine, because the worst case query time could be as high as n when all items hash into the same location. But when we apply the simple uniform hashing assumption, we get a much better bound, and this is much more realistic as well. As it turns out, there is a further improvement that we can achieve as well. But this will require us to use 2 hash functions instead of 1 hash function. So this is a very classic, well-known result called the power of 2 choices. Let me first state this result from the perspective of balls and bins. So we have n bins. They are indexed from 0 to n minus 1, and we have n balls. Each ball chooses 2 bins, both uniformly at random and independent of each other and independent of previous choices. And so let's say without loss of generality, bins I and j are chosen. And then we check the number of balls that are already present in I and j, because this process has been happening. Several balls have already been placed. So now we check to see the load on bins I and j. And we find out that one of the bins has fewer balls, and so we place our ball into the bin that has the fewer balls. And this is simply the power of 2 choices. For each ball, we simply probe 2 bins, and out of those 2 bins, we find the bin that has the fewer number of balls and place the current ball into that bin. And quite surprisingly, this small variation of the classic balls and bins gives us a much better max load, meaning a much better bound on the number of balls that is going to be found in the bin with the most number of balls. In fact, the max load is going to be at most ln n over ln 2 plus O of 1. Now that has to be contrasted with the previous bound that we got, which was 3 ln n over ln n. And so notice that this bound is exponentially smaller than the previous bound that we got. And of course, it's easy to see that this improvement can directly be applied in the context of chain hashing, provided we use 2 hash functions. And not surprisingly, this improved result is also quite applicable in the context of load balancing, cloud computing, and data center optimization, and so on and so forth as well.